In lab, you guys looked at how temperature affected pressure, and a guy named Amonton did this a long time ago. In fact, there's three gas laws that all go together. There's Boyles Law, Charles's Law, and Amonton's Law. Boyles Law talks about volume and pressure. Charles's Law talks about volume and temperature, and Amonton's Law talks about pressure and temperature. And what you guys saw in lab and what Amonton figured out was that temperature and pressure go together. If you increase the temperature of a gas, then the pressure is going to go up. If you decrease the temperature of a gas, the pressure is going to drop. And it follows this nice linear relationship. Your data might not look quite this linear, but it should have been fairly close to a straight line. Now let's think about why that happens. If you drop the temperature of something, that means those particles are slowing down, they're losing energy, and so they're going to hit the container walls with less force and less often. Remember, gas pressure is caused by these particles bouncing off the walls, smashing into the sides of their container. If they don't do that anymore, then there's no pressure on the walls. They slow down, the pressure goes down. Of course, if the particles stop altogether and they're no longer bouncing off the walls, then the particles have reached what we call absolute zero, the lowest possible temperature, because you can't get colder or slower than stopped particles. And we can use this graph to extend back down to zero pressure to figure out what temperature that would happen at. It turns out that happens at right around minus 273 degrees Celsius. That is equal to 0 Kelvin, or absolute zero, the temperature at which all particle motion stops. Now, there is a mathematical equation that states Amonton's law. It just says the initial pressure over the initial temperature is equal to the final pressure over the final temperature. Now, there is one caveat on this. Temp must be in Kelvin. Usually you're given temperature in degrees Celsius, so it's easy to go from Kelvin to degrees Celsius or degrees Celsius to Kelvin. Degrees Celsius plus 273 is equal to the temperature in kelvins. So here's an example problem. If a gas initially has a pressure of 270 kPa and it changes from 25 degrees, this is Celsius, 25 degrees Kelvin or 25 Kelvin would be way too cold. So when it changes from 25 degrees Celsius to 35 degrees Celsius, what is its final pressure? Well, we are given that it has an initial pressure, or P1, equal to 270 kPa. A final pressure is what we're looking for. Its initial temperature, T1, was 25 degrees Celsius. That is not Kelvin, so we're going to have to fix that. T2 is equal to 20 or 35 degrees Celsius. Again, not Kelvin, so we fix that. So to fix it, all we have to do is add 273, and this becomes 298 Kelvin, plus 273 here, and this becomes 308 Kelvin. Then we just have to use the equation right here. So P1, 270, over T1, 298, equals P2, we don't know, over T1, 308. Now to solve this, we're just going to end up multiplying both sides by 308 because that cancels and it leaves the P2 all by itself. So grab your calculator and do this math. 270 divided by 298 equals, and then multiply that times 308, and that equals 279. So P2 equals 279 kPa. This would be about what happens to your tire as it drives down the road. The pressure goes up a few kilopascals because the temperature of the tire goes up as it goes over the road.